So, welcome to our very first Mind in Vitro seminar. We plan to have more of these, for the next, I would say, 7 years. But we're super glad to have Brad Nelson here to help us kick it off. Brad is a professor of robotics and intelligent systems at ETH Zurich. And he has recently become the chief scientific office advisor of Science Robotics, which is, how many of you have read Science Robotics? You've probably heard of Science, right? So this is a specialty version of it for robotics, and it has a lot of really interesting things in it. He has over 30 years of experience in the field and has received a number of awards in robotics, nanotechnology, and biomedicine. Really broad array of work, and been one of the people that I've been following your work since I started working in robotics. You always do super cool, unique things. He serves on the advisory boards of a number of academic departments and research institutes across North America, Europe, and Asia. Professor Nelson has been the department head of the mechanical and process engineering at ETH twice. My condolences. As the department head myself, I could say that. The chairman of ETH Electron Microscopy Center, and a member of the Research Council of the Swiss National Science Foundation. He also serves on the boards of 3 Swiss companies and is a member of the Swiss Academy of Engineering. Before moving to Europe, he worked as an engineer at Honeywell and Motorola and served as a United States Peace Corps volunteer in Botswana. I doubt there's very many roboticists that could have this in their CV. And he has been a professor at the University of Minnesota and the University of Illinois, Chicago. And one thing that's not in this bio is he actually got his undergraduate degree here at the University of Illinois, Urbana-Champaign. And we're super glad to have him back here to help us kick off our Mind in Vitro seminar series.
Okay, thanks. Thank you very much, Nancy. Yeah, it's always nice to come back to UIUC. Again, they call it, when I was here, they just called it Illinois. Do they still call it that or what? I don't know. So. Okay. Yeah, I was here 40 years ago, more than 40 years ago. So it's a very different place, but still some of the old buildings around. But I'm going to talk today about the robotics part of micro and nano robots. Here we go, just some disclosure, some of the things I have financial interest in. I also disclose I have been able to work with a great team over the years. We usually keep around 40 people, 45 people in the group. I'm a director, my co-director is a physical chemist, Salvador Pane, and we together keep this going. And you'll see everything here is the work of a big team of a lot of diverse people that we're going to talk about. But the talk is talk I created over the past year, thinking about what I've been doing at ETH in the past 20 years. I came to ETH in 2002. It's just been over 20 years ago, and we started thinking immediately about how to make small micro and nano robots, small devices. And as we work in that field, we became naturally interested in the applications of it, which are primarily in healthcare. And so we became interested in the field of medical robotics. And I start off with this little advertisement I found online several years ago. And I think it says a lot. It's an advertisement from a hospital down near Miami, Florida. It has a surgeon, a doctor with a robot arm photoshopped onto him or her, and it says 1 part surgeon, 1 part machine, both parts amazing. And what they're talking about, this is robotic surgery now at Palmetto General Hospital, and they're telling the general public, you should come to our hospital because we have the coolest technology and we're going to get operated on by robots. So I think the public's very accepting of this. Intuitive Surgical, the Da Vinci system has, there's over 5,000 out there right now. Well over 10 million procedures have been performed on them, by them around the world. I'm guessing there's some very, very close to us here in Champaign-Urbana. It's a real success story. And so a lot of folks have tried to jump into this space because Intuitive Surgical is a very successful company financially. More and more doctors are embracing the technology. Certainly hospitals see that it's something they need to have because the best doctors want to be using these, the ones at the forefront of the field. And so there have been a lot of efforts to get into this, a lot of spin-offs, a lot of investment, a lot of some successes, a lot more failures. That's the way startups go. But they're looking at new applications and how to get into this field. But there's a couple trends in the field lately that I think are quite interesting. One is from this company called Auris Health. They're out of California. They were purchased a few years ago by Johnson & Johnson for $3.6 billion. And they built this, I think it's around a 4.3 millimeter diameter endoscope. So that little, this little thing here, it's got a camera in it. It can take little biopsies, and what it's designed to do is the surgeon controls it with this Xbox-like controller to go deep into your lungs to take biopsies. Intuitive Surgical has another system, the Ion system, which is a little bit smaller, a 3 millimeter diameter catheter, smart catheter they call it. But the trends are in what we see in these two systems are smaller and smaller endoluminal devices. That is, devices that go in these lumen, like your gastrointestinal tract, into the bronchi in your lungs, or into your veins, your blood vessels, guided along more tortuous paths. Now, there's a limit to how small you can get these, and I just spent. Let's see, it's Friday, so it was earlier this week, a couple days with an engineer who spent 8 years there designing the small ion system. These are extremely difficult systems to make small and make precise and work well. You can't get much smaller than this. But we do see trends in people trying to find disease smaller, or sooner and quicker. And so where might the technology be heading? Well, it could be heading in the future would be trying to break that tether and let these devices move in the body free floating. And so I think it's interesting that the big companies, people like Johnson & Johnson, people like Intuitive Surgical are moving in this direction, because this is where our group, as well as several other groups around the world, have been thinking for the last 15 to 20 years, trying to make small intelligent devices and understanding what some of the technology bottlenecks there are in that. So this is a graph out of a paper we published last year in annual reviews called Increasingly Intelligent Micromachines, that kind of gathers what's going on in the field and what some of the trends are. But what you see is, the first interesting devices, even though we started thinking about this really in 2003, was when we started mimicking bacteria and the way that the flagellated bacteria move through these tiny little flagella that they rotate. And as we started to understand that and appreciate some of the interesting physics of that, some of the reasons why bacteria evolved these rotary motors to help them swim when they need to be motile, things like E. coli, we started then thinking, how can we functionalize them? How can we make them do things that are interesting? We use a lot of 3D nanolithography and these types of things, nanoscribe, direct laser writing. Then we started moving into polymers, materials that can adapt their shape and reconfigurable devices. At the end of the talk, I'm going to focus a little bit on some of the programmable devices that we're creating. And what the most recent trends out of our group, and as well as others, have been now to try to put logic on some of these devices. And when I say it's microrobots, I'm talking about devices that are generally smaller. Well, they're all smaller than a millimeter in scale, often smaller than 100 microns on the width of a hair. So how can you get this kind of functionality on these kinds of devices? As Nancy said, I've been in the field a long time. I got my mechanical engineering degree here in 1984 and a PhD in robotics from Carnegie Mellon. So I've been working in a real roboticist in the sense of, I used to help, like when I was at Honeywell, try to figure out how to put robots on the factory floor and things like that. But when you go down this path, you find a lot of the problems aren't the classic robotics problems. They aren't the classic motion planning problems. A lot of folks look at this and say, well, what's robotics about what you're doing? And there's a lot of truth to that. There's a lot of materials in fabrication that come in. And when I first started building my first lab up at the University of Illinois, Chicago, I started learning MEMS and microfabrication and these kinds of things. and trying to bring that into the robotics arena. But luckily, I was able to add to my group a physical chemist who runs a whole group, subgroup focused on the types of materials and fabrications problems we have. But one of the things I point out is there's a lot of material constraints here as we move into the medical domain, because we have to think about using biocompatible materials, preferably biodegradable materials if they're going to stay in the body, and that dramatically limits your material selection, and it also limits then the capabilities of your robot. And so you have to take these things into account and be aware of those. One of the key challenges as we were going down this path was, how are you going to power these devices? They're small. They have, as you're aware, volume scales with a third power of length. So if I make something 10 times smaller, its volume goes down by 1,000. And what that means is you're not going to be able to store much energy on these things. And so we started thinking about ways we could bring in external energy. And the first thing you think about is using some kind of magnetic fields and magnetic materials like iron. That you can move inside the body. And so we looked at generating fields and gradients and rotating fields, and I have a whole class on microrobotics that goes into the physics of why we want different, what some of the motivations here are. Other folks have looked at chemical approaches. You're looking at catalytic motors. Unfortunately, a lot of these motors are driven by toxic fuels. This one's driven by hydrogen peroxide, which is something you don't want in your body. There's even papers out there on hydrazine, which is super toxic. But they're interesting. We can make these small things move. Other folks have been looking at light-driven robots using kind of phototactic kinds of behaviors. One of the other areas that's been interesting and more groups are getting into are using acoustics and ultrasound. So we're very comfortable getting in magnetic resonance imaging machines. We know that's safe for using magnetics, and also we use a lot of ultrasound, of course, to look inside of our body. Often if you're pregnant, that's one of the first things they'll do is check to find the heartbeat and things like that. So, but we can also use that energy and collect it in order to drive our devices. And so we've been thinking a lot about that, but still over the years we've focused primarily on using magnetics. And so that's what I want to talk about, is some of our work in this field. So I want to go over just a little bit of physics here to start with, okay? And there's two fundamental equations we have to be aware of, the torque and the force equations that are generated by magnetic fields. And you'll see the terms up there. There's a V term for volume, and that should tell you something right away. That's something scary when you get at small scales. When you see that, you're like, okay, that's going to govern a lot of the physics that'll predominate. The M stands for the magnetization, and that's a function of the material. We typically use iron, but there's other materials. There's basically three materials that have magnetic properties: iron, nickel, and cobalt. And then their alloys. Iron has the nicest biocompatible properties. And then there's the field and the field gradients. So torques are most easily understood if I can have some field, some magnetic field represented by these flux lines here, and I put my microrobot in it, representing my microrobot by this magnetic dipole with a north and a south pole. It will feel a torque according to that cross product with the field, and will align itself with there. So that's like a compass needle in the Earth's magnetic field, the same kind of physics as that. Forces are a little bit different because they've got the gradient term on there. And that means that we're going to be able to translate our device. It's going to move in the direction of the increasing flux density. So you'll see that it's aligned with the field, but then we can generate forces by changing that flux density. And so now what we became interested right away was, how do we generate these fields and these field gradients? What are some of the physics of that? And so what I want to convince you of is this is fundamentally a robotics problem. And this is where, when I say the robotics part of micro nano robotics, this is one of the parts that I think robotics people, like motion planning people and folks that come from the field like I do, have a fundamental contribution to make there. So how do you generate magnetic fields? Well, there's really two ways to do it fundamentally. One is you get a permanent magnet, like a bar magnet. Like I think as kids we've all played with these, and it's got a north and a south pole. There are no magnetic monopoles. And you've got flux lines that go from the north to the south, and these contain some kind of magnetic energy, and if you put a body near them that has magnetic properties, it's going to feel that force. But it's static. You can't turn it on, you can't turn it off. But what you can do is you can put it on the end of a robot arm and you can move it around. And so that's one way you can generate varying fields and field gradients is by actually physically moving that magnet. And that's what somebody like Pietro Valdestri, who's at the University of Leeds, did and published this nice paper where he was looking at moving colonoscopes. This is in the large intestine, moving devices that have a magnetic tip and moving them in your large intestine. Xiaowei Zhao from MIT has also did that. He recently published a paper in Science Robotics where we've got a robot arm with a permanent magnet on the end of it. And he's using it to guide catheters in the brain for treating neurovascular disease. And there's some advantages to using permanent magnets. One is that they're relatively cheap and they're fairly strong. You can, with the right material, generally neodymium iron boron alloys, you can create relatively high fields. But there's also some disadvantages in that you have to move them, and they also, you can't turn them off. So we've been thinking for quite some time about electromagnets, and electromagnets are relatively simple. You take a copper coil, for instance, you wind it often around a soft magnetic core, often iron, and as you're putting current in it, you generate the field. And the advantage here is that I can modulate that current. I can increase it and increase the strength of the field. I can do more than that. I can also reverse it and create change the direction of the dipole without anything moving other than those electrons. So there's something more inherently more safe about that. And the other thing that's important is that I can turn it off. So I can remove the field. If something goes wrong, I can just shut it off. So we've thought a lot over the years about how to generate fields and field gradients using electromagnets. And we've thought a lot about how to wind electromagnets and how to wind these cores. And so it's a lot more than just spinning some copper wire around a piece of iron. There's a lot more to it than that. One of the real challenge of an electromagnet, the fundamental problem comes down to thermodynamics. What you want to do is put as much current as you can, but you know these wires have resistance, they heat up, and things can start to melt. You also have limits on how much current you can get and how much your power drives can handle. But if you think about the problem and you think about the heat transfer and removing it, you can do quite a bit of interesting property capabilities here. And so we've thought a lot about it, filed a patent on a particular winding that allows us to increase the power density, we think by about a factor of 5, which means we can get 5 times stronger fields than you can from a traditional electromagnet. But we don't think about using just a single electromagnet. Of course, we use a configuration of them. So I'm going to put several around the workspace, and then I can control each of those individually. And remember, none of them are going to have to move. So they're going to sit there, and I'm just going to control the current in each one of them. One of the things about magnetic fields you're aware of is the fields superpose. So they just add up. So as I have all of my in this case, 8 coils that I've got down here in this workspace, I can linearly superimpose these fields. And one of the things we were able to discover around 12 years ago or so, this is with Jake Abbott when he was doing a postdoc in my group, was that we can cast this whole problem in a robotics framework. So I've got in this equation here, this is my input to my system. It represents the currents from the N electromagnets, in this case 8. And then it goes through this mapping. The mapping has in it the magnetization. That's a function of my microrobot, the material it's using, whether it's iron or nickel or cobalt or whatever. And then its position in the workspace. And then with that, I can generate the fields and the field gradients, which gives me the torques and the forces. And so when you look at that, you recognize as a robotics person, you're going to, from an introduction to robotics, you're going to recognize right away that that looks very much like a manipulator Jacobian. And so when we saw that and understood how to cast it in that framework, all of a sudden we realized we can bring about 50 or 60 years of work in robot manipulator design to bear on the problem. Because with a manipulator, as a robotics, any roboticist realizes, you know, if we think about the input to my robot arm, which is going to be, the velocities of each one of the joints of each one of the motors, typically 6, but it can be more or less depending on what you want to do. We get end effector motion, we get the Cartesian motion. Similarly, with my electromagnetic configuration, I can have, in this case, I've got 3 electromagnets, these 3 here. The input are the 3 currents, and the output of that then are the fields and the field gradients that I can generate. And we've got that same framework that we can work with here. And so now we've got problems that we can, the traditional robotics folks have worked on, we can bring in and look at from an electromagnetic perspective. And so we started thinking about this, and I showed that first system with 8 electromagnets. Here's there's kind of a copy of that system or a duplication of that system, only at a much larger scale. In this case, large enough that you could lie in it. And we did a lot of modeling and a lot of numerical simulations of this, and arrived at just sort of a heuristic that 8 seemed to work. As a robotics and mechatronics person, and if I think of my microrobots as having 5 degrees of freedom, that is X, Y, Z, and then pointing along 2 directions. We typically don't get this direction, those 5 degrees of freedom. We would think, yeah, I probably need 5 electromagnets to do that. But there's a coupling, and it's not clear that coupling. It's not obvious that between the coil or between the gradients and the fields. And so we started looking at this problem in more detail, more beyond just numerical simulations. And when Andrew Petrusko was in my group, he was Jake Abbott's PhD student. Remember, he's the guy who helped us figure out how to put this in the framework. And then Andrew, we sat down and came up with a paper that allowed us to put a minimum bound on given a task that I want to perform, what's the minimum number of electromagnets I want. And being able to put a minimum bound on something is really important, of course, for design, because it tells you right away, don't try to optimize it anymore. You're not going to be able to. We can mathematically show that we're not going to be able to go, for instance, less than 8 if we want to get the full 5 degrees of freedom. But we started thinking about this in more depth. And so Quentin Baylor, who's a scientist in my group now, started looking at this from a more classic robotic manipulator problem, and thinking about how do we define the workspace of an electromagnetic navigation system. Workspace is a fundamental concept of a robot manipulator. Where can it reach? How fast can it go? How much force and torque can it generate in that? But nobody really looked at this from an electromagnet standpoint. So if I have a simple system with 2 electromagnets, here's one here and one here, I can generate a field in this area. I've got my microrobot or my little dipole here. I've got some point in my workspace, and I have to realize that I'm going to say that point P belongs to the workspace if the tasks that needs to be performed is feasible within that defined current range. And the fact of the matter is, as I mentioned before, electromagnets have bounds on how much current we can put in them before things start to melt, or maybe have limits on my power supply or my current drives. So I've got some inherent bounds on that. So if I think about this from a robot perspective, or from a more mathematical perspective, I'm going to put a limit in this case on just the minimum and maximum current I'm going to put in each one of my electromagnets. There can be other constraints you can think of. Maybe there's a maximum amount of current that my entire system can deliver, or it can be more complicated. But for simplicity purposes, let's look at it this way. And then by pumping this through that actuation matrix I showed you before that contained the magnetization of the object and its position in the workspace, I can figure out at some point P, at each point in the workspace, what is the available fields or field gradients that I have. And this is a simple 2D example. And then I can look at my task that I need. And I can say, at point P, for one task, I'm going to need these kinds of fields, and another, maybe for another task, I'm going to need these other fields. So I've either got a feasible or an infeasible task, and I need to then can look at it that way and think about what I want to do to move my microrobot to some location, or to have it perform some kind of a procedure. Is it possible given my system? If it's not possible, I have to rethink my system. And so then this leads to the concept of workspace metrics. And how can I define how good of a manipulation capability my electromagnetic navigation system has? And this is something that the robotics community's thought about for 40 years or more. One of the classic metrics is manipulability. And so we went back to that early work, and a big part of inspiration for me was Professor Yoshikawa's paper in 1985 on the manipulability of robot mechanisms. That was the time I finished here in 1984 and moved up to Minnesota to do a master's degree. And my master's thesis, my advisor had told me, he says, given a, if we have a manipulator and we have some sequence of assembly tasks we need to do in the manipulator workspace, where would be the optimal place to put the manipulator to perform those? And at the time, I really had no idea how to address this. I was thinking of joint limits or these kinds of things. But when this paper came out in IJRR, all of a sudden it just was crystal clear that this is the kind of metric that really helped us understand the assembly problem and where would be the optimal place to do some kind of a manipulation within a robot workspace. So we started thinking about this same kind of thing for electromagnetic navigation systems that are generating fields and gradients. And Quentin came up with this idea of defining a new metric he calls the D to A distance. And so A, remember, is the available field and field gradients that I have. And D is going to be what I'm required for a certain task. And then by measuring that, or by estimating that distance, then that distance from the task requirements to the availability that the system has is going to give me a metric that we can use for that. Now, this is all in 2D, and it's pretty clear, but now as we get into multiple dimensions, as any good robotics person knows, things start to get complicated and cloudy, but luckily this extends, and so we can extend this to higher dimension systems. But even at two dimensions, it gets interesting for us, because if we take this system here, I've got two electromagnets. This is theta equals 90 is the configuration I have here. And I can start asking, what happens if I start adjusting that angle between them and I move them? What happens to the workspace and how does it look? And there's things happen that aren't intuitive, like I start getting voids in the workspace. In other words, now I get some interesting topology issues, and how do you discretize or look at interval analysis, these kinds of things that come in. As I bring these closer together, I'm starting to see a more continuous workspace. As I move them farther apart, it changes that way, and I think that's not necessarily intuitive even for the two-dimensional case, right? The simple case, the way it's going to work. But what became even less intuitive to me was when I just said, what if I took my two electromagnets and I put them on the same side? I made them linearly dependent. That I would, whenever I have sensors, I like to get, good coverage of the workspace. But when I put them together, we started getting a better workspace, and then we can start to look at how we move them apart and how that workspace changes. And so these things become, like I said, I think non-intuitive, and I always like this kind of results, right? Where I look at it and I'm like, okay, now I see it, but before I did this, I didn't quite see it. And I think this helps us along our path of designing our electromagnetic navigation systems. And like I said, these extend to higher order systems. We can look at 3-coil systems, 8-coil systems, or whatever, and start then defining the suitability of the particular configuration we have. So this helps us design our systems and understand why they work the way they do, but it also helps us control our systems and allows us to do things like, take this little 1.5 millimeter long little nickel microrobot and very precisely move it with 5 degrees of freedom in its workspace. This is something we first realized back in 2010, and we patented it and have licensed that patent. But before that, nobody had really been able to control these. So that was 2009 was when we first got the system to work. That's our first system. And then we started thinking about electromagnetic navigation system design over the years and made several of them. We've gone smaller, so now we have systems that are that can go under microscopes and you can use to interact with cells. I mentioned the larger system where you can do large animals, big enough for a human to lay in. We've even gone to clinical systems, but more recently we've been looking at thinking as we translate out of the lab and into the hospitals that maybe we need to start thinking about more portable systems. We've been thinking that way. The other thing as we went down the microrobot path that became apparent to us was it's a hard sell to tell my doctor, oh, I've got this really great microrobot, you should put it in somebody's body and let it move around. But what we realized maybe was a little bit of an easier way to get in was if we started thinking about our microrobot not as some untethered device, but we basically magnetize the tip of something like a catheter or an endoscope. And now it becomes quite similar to what surgeons are used to working with. And And this little animation here kind of shows the complexity of these fields. This is a 3-coil system. You can see the flux lines coming out of each of the coils, and depending on the amount of current in each one of those coils, we can get these complicated fields, complicated field gradients that are generating these interesting curves and interesting motions that give us a lot of dexterity on the tip. And so now thinking back about the workspace of our electromagnetic navigation system, the forces and torques that we can generate within there, and then modeling this, and we do a lot of modeling with the SOFA framework, the soft robotic open source framework that gives us pretty accurate results. We can start understanding what kind of fields and gradients we need in order to achieve our tasks. And so that's basically where we've been going down this path. So I mentioned we made a clinical system. We started looking at a system that a whole person could go inside. And in this case, what we were looking at treating was cardiac arrhythmias. So this was patients who suffer from heart arrhythmias. One of the therapies for that is to basically perform ablation within the beating heart in order to kind of reset the electrical system in a way. And so this is our clinical system. It's in a hospital outside of Zurich. And what you see is our electromagnetic navigation system is over here. But one of the nice things about it is we can actually pull it apart. It actually is on rails and moves apart. You prep the patient then. This is the 2.3 millimeter diameter ablation catheter that goes in the femoral artery and up into the heart, where the ablation procedure is done on a patient while he or she is awake. And then this is where the surgeon is performing the surgery, electrophysiologist. One of the nice things they like about it is you'll notice this is a fluoroscope. This is an X-ray system for looking in the patient while this is going on. And now the surgeon is actually protected from those harmful X-rays being removed from it. This is one of the days we did 7 patients with this system. This day there was a woman in there. This is Firat Duru. He's our electrophysiologist controlling the catheter with a joystick. He's looking here at a map. This represents a geometric map of the right atrium, the upper right chamber of this patient's heart, and he's planning. It's hard to see up here, but he's got some little dots that he's drawn on this, and this is where he wants to do the ablation to try to treat the arrhythmia that this particular patient has. She's by herself in the operating room, in the cath lab, awake while this is going on. And we learned a lot of things. First of all, the system functions very reliably. We've had some of these systems going for over 10, 12 years now. And you start them, we don't have any moving parts except a pump to get the cooling fluid to go through. They work pretty well. Takes a little getting used to. We've got to train the users. When we did these experiments, we were using commercial off-the-shelf catheters for this, and we realized that we needed to start thinking about catheter design and the stiffness of that. And the other thing that became quite apparent is that these systems are too large. This system weighs about 7 tons. And to convince a hospital to put that in, they're going to have to remodel, and it's a big investment for them. So we started rethinking that problem and rethinking the workflow and the purchasing, basically purchasing, workflow integration, all these things that you have to in a hospital. We're not the only people to think of using magnets to guide things in the body. The first paper that I know on guiding catheters is from 1951 from a person called Hans Thielander out of Germany. There's a company, Stereotaxis, that's out of St. Louis, Missouri, that's been on the market for over 20 years now. They've got 150 systems or so out there and have done over 1,000 procedures with them, I believe. What they have is a permanent magnet system. So this is their older system, and this is the newer system that just came out a couple years ago. These are 290 kilograms. So these are over 600-pound magnets that move around. So they're slow, and you can't turn them off. But there's a lot of surgeons who use these and like the system. I mentioned our system, which we call the Aeon Focus, that's quite heavy, but at least you can turn it off because it's electromagnets. You pull it apart and you can use the operating room normally. This has to have a dedicated operating room. But what we've been working on more recently has been a portable system, something that can be wheeled in and out of the operating room quite readily. And this is something we call a Navion. It's a 350 kilogram system. It's on wheels. A single person can move it in. It can be set up in less than 10 minutes because we've done it in our couple hospitals in Zurich. We also spend a lot of time designing the specialized magnetic catheters, endoscopes, and guide wires. One of the other things I didn't mention is there's a mechanical advancer that pushes this catheter in and out of the vasculature. And then it's all ROS-based, all the software, at least the research systems are. The clinical systems, we have to rewrite all the software because of regulatory issues. And this is a system we recently installed in Hong Kong. We have a work with the Chinese University of Hong Kong, a Hong Kong government-funded project. There's a center there called the Multi-Scale Medical Robotics Center at the Hong Kong Science and Technology Park, and you'll see our Navion there. This is a Siemens Zigo system. Basically, it's a C-arm. Here's the emitter. Here's the detector on a big. It's a C-arm on a big robot arm to move around, and so we've integrated it into that system there, and are just starting. I was just there in October. We were installing it, and we're just starting to do experiments there with it. But we've changed our focus a little bit from cardiac ablation, talking about how we can treat heart arrhythmias, to stroke. And stroke is, if you're not aware, is the second leading cause of death. There's several different kinds of stroke, but the most common stroke, 87% of strokes, are from blood clots, the clots that get stuck in the brain, thrombosis. And so one of the things about stroke that's quite important, it's treated somewhat similarly to the ablation problem, where you put the catheter into typically in the femoral artery, but this time you snake it up over the aortic arch and go into the brain with it, is you need to get that blood clot out as soon as possible. The neurosurgeons or interventional neuroradiologists who do this say time is brain, and the longer you wait, the more brain cells that are going to die, and the less your chance of having a full recovery are. And it's been recently shown in the past 10, 15 years that mechanical thrombectomies, that is going up and mechanically removing the blood clot, is called for in many, many of these cases. And so there's been a lot of interest in making these more dexterous devices that can move up into the brain to do this. So it's a huge issue all around the world, and we're trying to figure out how we can help do this quicker and get them in. Get this system in. The way it's currently done, the way interventional neuroradiologists currently do this, is they take a catheter or a guide wire. They typically have a bend on it, and they'll have a whole cabinet of these with different bends, and they'll snake one up, and they push, they pull, and they rotate that while they're looking at it under X-ray, while looking at it under X-rays, to try to get it into snake it up through the neurovascular into the right blood vessel where the blood clot is. And from a robotic standpoint, this is a classic non-collocation problem, right? The task is up here, but the actuators are all acting down here in the femoral artery. And so this is a real challenge. But what we are able to do with our system is now we're exerting those forces and torques at the tip of the catheter, or the tip of the guide wire. And this is at my lab back in Zurich, downstairs, and you'll see we've got a PlayStation controller. In this case, that's an X-ray of a 3D printed aorta, so that's the aortic arch, and then going up into the carotid arteries, deep into the brain. What you see in the upper left here is our kind of phantom. This is a cardiovascular phantom, human-sized, the patient, and so this what the person doing the experiment here is actually guiding the very tip and exerting that instead of there's still the advancer pushing it and pulling it, but the steering is all done right at the end point, and that makes it a much more intuitive and easier manipulation problem. And I think this next video kind of illustrates that really good, where on the left is the magnetic guidance, and on the right is the traditional push, pull, rotate approach, and you can see how quicker it is, how much easier it is, how much more intuitive it is to guide this catheter. It looks simple, but there's a lot of math, there's a lot of physics, there's a lot of challenges in how to generate these fancy fields and to get it to bend properly. And by rethinking catheters a little bit, we can actually create, I think, the world's most torturous catheters that can reach, can go through a number of twists and turns, and there's simply not a catheter on the market that even comes close to what you see on the bottom here. At most, you can get a few turns in, even with simple magnetic devices. So we're able to with that. And of course, as we go through and design and develop these things, we're always filing patents, IP, and trying to protect this so that if we do try to get it out of the lab and into the clinic, there's some motivation for the investors to get involved there. This is our interventional neuroradiologist, Philip Gruber, from a Kantonsspital Aarau, a canton next to Zurich, and he works at a stroke center there. This is with a large animal, in this case a pig, and he's got a controller, and what he's doing is guiding this. It's a 2 French, or about a 700, 800 micron diameter catheter. You see it going up. This is into the brain of this large animal. And he's able to select whichever one of those branches he wants to go in. He's pushing it up, and then guiding the tip quite precisely. And so it's very intuitive. To tell you, Philip has worked for 7 years, trained for 7 years before he was just allowed in the last year or two to supervise his own surgeries, because it's an art getting these to work. It takes a lot of dexterity. What his real judgment is understanding the physiology of what's going on, but getting the skills of manipulating that catheter is a challenge as well. One thing he was particularly excited about is, if you look here on my, let's see. You'll notice this right down here on the bottom, just below the circle. There's this bend here, and he thought that this is a problem I don't think I could tackle given my current technology. He's navigating from a large artery into a very small artery, and that sharp turn is extremely difficult to make. And so, let's see if I can get that going here. There we go. And so you'll see in that corner, you'll see that little magnetically tipped guide wire. It's basically a robot with a little tether on the end of it. And he's pushing it up from the large, and then trying to fish it around into there. And there's really not, as he told us, there's not a technology he has that he thinks he could do that currently. So we were excited about being able to make these kinds of turns, right? But you'll notice those veins and arteries. Those are what they call those roadmaps, literally so the white, the clear, the white part. Those are what they call the roadmap. And basically, what they do periodically during the surgery is they'll inject a contrast agent, often something with iodine in it, and it will look very, very bright in the X-ray image. Actually, it looks dark, but it turns out bright the way they do the image processing. And that roadmap then lets them plan. So this is something you can do with planning, is figuring out what is the best plan, what's the best route to take to these, what are some of the parameters on how you might guide these. But you'll also notice it looks like the catheter is going outside of that, and that's because during the procedure the veins can actually move, and so it's actually in the veins, but from when the roadmap was taken to as it moved as he's doing the operation, you can move those around a little bit. So there's a planning issue for you there. So this animation kind of gives you a sense of the way the system works. We've got our Navion again, 350 kilograms. You wheel it in and out. It just needs some cooling, some water for cooling, nothing special, and a special plug in the wall. We've got our catheter, in this case a guide wire that is the first thing to go in, that kind of finds the path to where you want to go, just showing the complexity of the fields, the flux lines that are coming out of our electromagnets to guide that. And there's it's interesting mathematics. You can go back 150 years to some results on some of this. Here's our patient whose head is near that. You want to be close to your electromagnets. That's the advancer at the femoral artery of the patient where the catheter goes in. There's an interface, one of the user interfaces by the bed, if the surgeon wants to do it there. And so first, the blue is the guide wire. That's small, and the job of that is just to get there. And then there's the working catheter goes over that. And in this case, it's called an aspiration catheter. But this is the aortic arch, and now the magnetic field is bending it up this artery. Continues going forward. This can be all under magnetic control, or it can be following, depending on where you are, and there can become some really torturous paths, and you've got bifurcations in there where you need to select where to go. That's the job of the neurosurgeon. Everybody's anatomy is a little different, but same basic morphology or similar morphologies. And then you can see that there's a blood clot right, it's almost there. Now we're doing a sharp turn and cranking up the field, and now that's where the blood clot is. So now the guide catheter is pulled out, and the aspiration catheter, basically just a little vacuum on it, sucks the thrombus out, and hopefully that's done rapidly, and the blood flow is restored, and minimal damage from the stroke occurs. The surgeon can be outside, or the surgeon can be kilometers away. We've controlled our system down in the lab from China. So in Zurich, we've controlled it from China, we've controlled it from Botswana, we've controlled it from the East Coast of the US, from all over Europe, and so it lends itself to telesurgery quite nicely. But we look at this as a platform technology. It's not just treating stroke or ablations, but we're looking at a number of other procedures. Giant aneurysms are big open spaces, and these are notoriously difficult to get catheters across. And so that's one of the things our system, we think, is quite good at, and that's the kind of feedback we've got. We also work, this is the project in Hong Kong, we work with gastroenterologists on small endoscopes that are 4 millimeters in diameter that can go into your stomach or all the way through your small intestine and are guided magnetically. One of the really interesting projects we've been on recently have been working with fetal surgeons that are doing in utero surgery on fetuses. In this case, these are twins in which one of the twins is getting too much blood and the other one's getting too little. And by ablating on the placenta particular blood vessels, they can balance out that. And that's, I've seen every surgery I see is fascinating, but when I saw fetal surgery for the first time, it's quite interesting. And there's a lot of challenges in getting a good view, getting in around the fetuses, depending on where the placenta is. So there's a lot of things we can do there, we think. So we're continuing down this path, trying to get our Navion, our system, through FDA approval so we can use it in clinics, and also looking at other uses for it. But we're still interested in microrobots. We still do a lot of our fundamental research is in trying to make more intelligent devices and trying to see where this might go. And so one of the things that we became interested in lately is how we might program these. Because all these devices are all kind of built, and you put them in, and the only thing you can do is change the magnetic fields and gradients to get them to move. But we were wondering, is there a way we could change their behavior? And so this is some work we did with Laura Heiderman. She's a physicist whose expertise is in nanomagnetism. And I learned some things from Laura I didn't know before. So if you're a physicist, into the physics of it, you know very, very small particles are super paramagnetic. That is, they're a single domain, and they very rapidly forget their magnetization. If you magnetize something, it forgets that it's magnetized. So they're essentially all soft. Now, if you have the right materials with hard magnetic properties at larger scales, there's magnetic domains that you create, and depending on the material, you can get certain materials that we call coercivity, but basically they're telling you is this soft something that's going to forget it's magnetized, or is it hard or permanent, it's going to remember its magnetization and not forget it. But there is a class of material, a class of shapes in the hundreds of nanometer range where that coercivity changes, not depending on the material, but depending on the shape and the size of it. So so I take this exact same, what we call a racetrack shape, and I change its size. I can change basically how hard or soft that magnet is. So I get these anisotropy curves. If you're familiar with your BH or MH curve, you recognize this. So at small scales, this basically means it's a soft material. It easily forgets it's magnetized. And at larger scales, it remembers. It takes a higher field for it to forget. And so working with Laura's group, we decided to add this to some of our soft microrobots and put these different material, these different shapes. We used E-beam lithography to pattern them in different shapes and create different coercivities using the same material, in this case cobalt. And so now what we can do, because the coercivity is different depending on how we pattern that. If we expose, for instance, we shoot a large field through it, then then these domains are all going to align here. If we shoot a smaller field, then this guy still remembers he's magnetized, whereas this guy flipped, and then I can do this in other directions. And so with this 4-panel system, I can actually come up with 16 different configurations that I can program in situ. So the same device I can get to behave in 16 different ways, and this is 4 of those shapes. So this is the same device with the same input, the same magnetic field, behaving differently depending on. So that's a kind of a method of programming in situ our device and changing its behavior as we want. So this is, I think, the first programmable microrobot that anybody has ever produced. It's kind of fun. I think there's a lot more to be done with it. But my, they were postdocs at the time. Now we're both professors. Jiawei Chu and Qianyun Huang are now out. I think Chu is at Cornell and Qianyun is at Peking University. But they thought about origami cranes. So then they created a micro origami crane and patterned it, different portions of it with different size nanomagnets. These are made out of cobalt, by the way. And then by programming them differently, they can get the same crane to behave differently. So that's scale bar is 40 microns. This guy's about 100 microns or so in size, very, very small. And here we were able to encode a kind of flapping behavior that's actuated magnetically. This is a turning kind of behavior, same device, but encoded differently now by switching the fields that we expose it to in different directions. This is a kind of an elegant hovering behavior. Now this is all, these things aren't really flying. I showed this once and somebody thought they were really flying. They're not, they're just, it's just an illustration. And then I think this is a side slipping. But we were able to with the same device, encode it. And so that's something that was new to the field when we published it, that nobody had been able to show before. So I think that was kind of fun. So just to wrap up here, micro and nanorobots, we still work on electromagnetism. It's our actuation method of choice. We think there's a lot of interesting things we can do with nanomagnetism. We're just scratching the surface on. But there's a lot to explore both fundamentally and theoretically. And I think robotics plays a key role in this. In the medical robotics, just to summarize, there's been success in the field. It's been embraced by healthcare in a lot of ways. I mean, there are criticisms of it, but overall, I think it's been embraced. But it takes a long time for ideas to get out of the lab and into the clinic, and the reasons are manyfold. Like robotics, like a lot of technologies, we underestimate the complexity of what we're trying to do. It's not just robotics that does that. I think I talked earlier about tissue engineering. We see genetic engineering, lots and lots of new technologies we think are going to get out there quickly, and they don't. Understanding the surgical workflow, understanding how hospitals work is key in getting these things through. The other thing is you got to have a strategy in this. If you want to get if somebody sends a paper in for a review, one of the ways to kill the paper is you say, oh, it's an incremental result. But incremental results are good in biomedical applications if you want to translate them, because you don't want to bring in radically new technologies, but you need to see how you're going to move it through the, you got to have a strategy to how you're going to do that, I guess is what I'm saying. And then also, it takes a lot of investment to get these things through, and so you've got to think about choosing the right things to work on that have potential business models. You got to think about patenting. You got to think about a lot of these issues, freedom to operate. These kinds of things have to come into play. But one of the questions that I've always thought is, will the discipline ever impact access to surgery worldwide? So these are, expensive technologies. Only it seems like rich countries afford them. What can we do with this technology worldwide? And I think one of the things I'm not sure people realize, but I mean, we all heard, we just, the Earth just passed, what, 8 billion people a couple of weeks ago, I think, officially, right? So it turns out, of those 8 billion people, about 5 billion of those people do not have access to safe, affordable surgical care. We do, but a lot of the world doesn't. But a third of human disease, it's estimated, is amenable to surgery. So all of a sudden, a lot of people can't be treated for the kinds of diseases that you could if you were in the right place and born in the right place. We hear a lot about HIV, tuberculosis, malaria. There's been a lot of important advances and a lot of lives have been saved, but that's just a small percentage of the disease, global disease burden out there. And so one of the things that it's been recognized now over the last 5 or 10 years has been that we really need to think about ways we can bring surgical techniques out of the first world and into what we call the global south, right? And so I think there's a couple things robotics maybe can help with here. One is remote telesurgery. I think particularly stroke. So this is one of the reasons we have a project back in Botswana now where, in fact, when I get back next week, I've got a team coming up from there to work with our system where we're trying to figure out, can we really start using these systems in remote places where it was about a year ago, I was in South Africa at a district clinic where if you showed up there for a stroke, you had an 8-hour truck ride to get to the nearest stroke center. So it just didn't even make sense to try to treat it in many ways. But the other thing that people talk about, and I don't want to oversell it at all, but the other thing is democratizing surgery. So I showed Philip Gruber, our interventional neuroradiologist, who had to study 7 years to do these procedures. But with appropriate technologies, a lot of procedures can require less training for surgeons. You're always going to need experts for the difficult cases, but maybe we can bring up the capabilities here. And there's just simply not enough surgeons in the world to perform these. Maybe there's a way we can democratize that. So I want to leave it there, and I thank you very much for your attention. Thank you.
So we can take some questions. You should be able to just speak. So
Yep. Yeah.
So you showed us that you can control the end of a wire.
Mm-hmm.
But how do you make sure that the entire wire conforms to certain classes? The end is not necessarily. I mean, if the entire wire is moving along some artery, the entire wire needs to come to the plastic.
Right.
That's the end point.
Yeah, so the way this is done is you push from the end, and then you have to design the catheter to have the appropriate stiffness.
maybe ask me to try to.
Oh, sure. Yeah, okay, yeah, for people online. So the question was, how do you ensure that the catheter, as it's moving through the body, is conforming to the path you want? And so the basic answer is it's inside of a lumen, so it can't get out of the vein. So that's the basic reason. And what we're doing is we're pushing it from the back and steering the tip, and then designing the stiffness of the catheter very precisely so that it's floppy when it needs to be floppy and it's stiff when it needs to be stiff. There's a big challenge with that. So yeah, thanks.
Hi, Brad. So you mentioned something like 3 millimeter or 2 millimeters, the size that's the tip of the probe that is going inside. So what limits the size? Why not getting smaller? Is it the material that is challenging, or just something?
Yeah, you're talking about like catheters and endoscopes?
Right, because some of the capillaries that are in the brain where some of these plaques get stuck, they're very, very small, right? And that becomes much bigger.
Yeah, so there's a couple things that limit. So these endoscopes that are out there right now they have inside of them pull wires. So that's the way they're bent. You pull one side or the other, and that bends it. And so there's limits to how small that can be. And you also have to have the working space in them. And often for endoscopes, you want a camera, some kind of a little chip in there. So there's a lot of stuff you got to put in there. So Monday had a long discussion just on this exact point with what's the limit. So Intuitive Surgical's catheter, I think, is about 3 or 3.5 millimeters in diameter that they use. But they spent a lot of time designing it to get that small. And one of their patents, and one of the things they need to do is they've got the endoscope in there, they've got the camera, and then they pull it out and are basically going blind and then doing the work through that blind. Whereas Auris had a 4.5 millimeter, 4.3 millimeter. They don't pull theirs out, but it's bigger, and they can't get as far. And so they're really at the limits of what they can do. We've gone down to 300 microns, but with no image sensors in them is what we've gone down to. So, yeah.
Is it working?
Yes.
Okay. Thank you. I had a question for the micro catheter navigation. So what's the role of the flow in there? Is it something you can take advantage of, or is it just in the way, or?
That's a great question. Mostly the flow is ignored for now. However, there's some work, and Selman has been working on this, for one thing, are flow-directed catheters. So they basically take tiny little ribbons with a little magnet at the tip, and you design it, and you can then guide it using the flow, or at least let it pull it through, and then you give it a pulse of magnetic field and move it down the bifurcations. So there's a few different groups that have worked on it. We actually, I've got a PhD student who's been looking at this for a few years as well. So you can use the flow to your advantage. The other thing is the flow is a challenge too, because if you have microrobots, of course, they get washed away, and so then we've got ideas there too. So, yeah.
Thank you.
But Howard Stone looked at this a lot, and things that go up against flow. So. Yes.
Yeah, I'll speak up.
Okay.
You mentioned that the roadmap.
Yeah.
The culture. So you mentioned that it's kind of similar between the different groups. Is there any learning experience happening? Is there any situation in the education student has
Yeah.
experience?
So I think there's a lot of learning that goes on with surgeons who use roadmaps during these procedures, because basically you have a catheter you put near this near the area you're interested in, and you release contrast agent periodically, and then you shoot the patient with X-rays, and you try to find where it went, and you look, and then you create that roadmap we said. And as I mentioned, that roadmap changes depending on as you're in there moving around. The vein can move, so you think where the roadmap is, all of a sudden it looks like your catheter has gone outside, but it hasn't. It's that the roadmap is no longer up to date. But the other thing, I think a lot of the learning is in looking at these X-rays and trying to figure out the tortuosity of the vein and understanding that. So what we showed you was a single C-arm that's just giving you a single view, but you can also have a biplanar one, and you can get a right-angle view of that. But there's still a lot of knowledge that surgeons bring in there, and I think that's what they really bring to the table, is understanding everything that's going on, because it's much more complicated than it looks. And everybody's anatomy, there's a similarity, but there's a lot of differences in anatomies as well, and recognizing that right away is important. Yes?
You mentioned that you did some bio-inspired design, like flagella, Nicola, and things. And that one of the limits of the typical casing is basically that you're trying to embed logic into your system.
Yeah.
So I was wondering if you're working, or if you're considering working on engineering bacteria directly to implement this logic, and to basically have like robotic bacteria and to do the same kind of things.
Yeah. So there's the question is about bio-inspired design and devices and incorporating logic into these. When we're thinking of logic, we're inspired a lot by people like John Rogers, who's creating these disposable technologies and being able to put transistors, pattern them on foldable devices and having them kind of just disappear in the body. So we have a project on that right now with a group from Italy that we're working on, where you can start putting some logic in it that way. But I think there's a deeper way of thinking about it as well, which we aren't doing right now, but that is trying to incorporate logic somehow in the material itself and having it behave in those ways. But I'm not sure how to start that problem. So, but good point. I think we could do that. So.
Question.
Yep.
That they want to ask. Well, why don't you ask it?
Question online is, in atrial fibrillation ablation, the catheter needs to puncture the septum between the right and left atrium. Does it allow for force feedback? By Girish Krishnan.
Right. So if you want to go, if you want to go into the left atrium, like you said, you want to isolate the pulmonary veins, and to do that, you go do a transeptal puncture across the septum, And I don't think force feedback is so important for that. What force feedback is important for is that when you do the ablation, you want a good contact between the tissue and the ablation catheter. And that force is important. And so there are force sensing catheters out there. There was a company out of Switzerland, actually out of Lausanne, I think it's called Endosense, were bought by St. Jude Medical a while ago, where they have a force sensing catheter for that. And what I'm told by the electrophysiologists who run the big groups like the one at Penn, where there's 17 electrophysiologists, when the young electrophysiologists use these force sensing catheters, they keep using them. They like them. It gives them confidence that they're making a good contact with the tissue. And I think that's where the force sensing comes in. And also I hear that a lot from neurovascular surgeons as well. They would like to know the force interactions with the veins as they're performing the procedures.
So as we are exposing like human bodies to the magnetic field to move these devices inside, so are there any side effects? Because blood and all also contains iron and other metallic elements. So when they are exposed to these directional fields, so are there any studies or something?
Good question. No, it's a very good question. So the fields we're using are about 10 to 100 times lower than magnetic resonance imaging fields. So if you've ever been in an MRI donut and had an MRI done on you, you're exposed to much, much higher fields. So the danger with magnetic fields is more in the frequency. If they're too high frequency, then those can cause problems, but we're well below the frequency. So this is, I think there are good, well-known standards on what's acceptable and what's not. So we'll make sure we're within those, but you have to watch out for that, that's for sure.
I have a question. I'm not an engineer, but potentially a patient, I guess. I didn't see on any of the slides for application on gynecological issues. They may not be, life or death situations, but a quality of life definitely.
Right.
Is that?
Yeah, I gave a talk at a gynecology conference a couple summers ago in France, so there are, needs there. I mean, I've talked to folks about implanting. They have little capsules, for instance, for in vitro fertilization, and there are some really challenging bends to get up, like through the uterus and up to the implantation. And so we've talked about these kinds of things, and these are the kind of projects we get going often when we have a doctor who comes to us with an idea. I'll have one of my PhD students or postdocs grab a master's student who's doing a thesis and say, "Oh, take a look at this for 6 months and see if we can do something." So I think these are, if we find the right partner, we're happy to take a look at those, and then we see if there's any, patents to be filed. What's the business case? Does it make sense to go further with that or not? And that's one of the things. We got this company, Nanoflex Robotics, and they're looking at neurovascular, but what they're doing is putting all the fundamental devices through FDA, so then you could hopefully move it over to something else if you do that. So, yeah. Oh.
So I really appreciated that this talk kind of captures the whole life cycle of research.
Yeah.
Sorry.
Oh, let me just see if you. Yeah, that was it.
Hi. So I really appreciated that this talk captured like the entire life cycle of research, from science in the lab to a production of a product that impacts people's lives. But my question is actually going to be about the last thing that you presented on, the Microrobots, which maybe we can't use in medical robotics yet. I was wondering, I've seen this like crane actuation mechanism in the context of shape memory alloys like nitinol wiring, and I was wondering if you've ever combined kind of material properties, like these different kinds of material properties, thermal actuation versus electromagnetic actuation versus maybe some other type of actuation, to increase the number of degrees of freedom of mobility or motility.
Yeah. That's a good question, good point. So one of the things that we look at is materials where we can modulate the stiffness. Because if you're snaking something up through your a lumen or something, there are times when you want it to be very flexible so you can go along sharp turns, but then there's times when you want it to be stiff so you can inject something or grab a biopsy. So we look at low melting point alloys, things that melt just around body temperature, so you can heat them up or cool them down to change their stiffness, or polymers that have a glass transition temperature around there. Shape memory alloys, I haven't looked at those. I mean, the problem with shape memory alloys, they get hot, they get really hot, and you've got limits to how fast you want them, or how hot you can make things in the body. They tend to be slow. We do use nitinol wires, but that's just because they're super elasticity. They've got that nice flat curve, but it's not the actuation capabilities. But there are people looking at that. I mean, I think Jadav Desai at Georgia Tech has been looking at shape memory alloys for some of these and some of that. So I think these are certainly possibilities, and you find some papers out there, I think, on that. So, but there's a lot of materials you can bring in. But like I said, you've got to think about biocompatibility. With a lot of these, if they're catheters, you just need to coat them so you can bring them out. But there's a lot of possibilities, I think. So. Yep.
Like decision making being done by on a software level, like when you have a catheter in a human body. Like I guess, for example, if there's like a high degree of precision required, like would the surgeon have to like be like good at manipulating the catheter, and like they just have to like have that level of precision, or is there anything that's like controlled by on a software level?
Yeah, so I think this is a $1 billion question. So certainly on the roadmap for the future of surgery, not the roadmap in your body that we were talking about, but the roadmap for where medical robotics is going, is you will find, certainly what will happen in the future is you will see some of these kinds of procedures being automated, and the surgeon will be guiding them, but then you've got some kind of image recognition, some kind of visual servoing approach that's going to be able to do this perhaps better than the surgeon can visualize these. And also some of these spaces are kind of non-intuitive when you're generating fields and all that. So if you took that out of the hands of the surgeon, you could do some benefits. Now the question is, how are the regulatory bodies going to look at that, right? And so that's what's not clear right now. And we've got these things in the regulatory in Europe called the notified bodies, and they're the ones who make these decisions. These individuals will decide on things, and they don't know what to do, so they're not going to make decisions. But that's where we want to go. And the question is, how are we going to get there, and when are we going to get there, I think. So, yeah.
Yeah, I had that question too. So let's take the question from Zhao on Zoom.
Thank you. Hi, Professor. Very interesting talk. So my question is more about like the microrobots and nanorobots, right? So as the robots get smaller, the square cube law kind of tells you that their surface area is going to be more relevant than their weight, right? And at some point, the viscous forces, say on the human blood, becomes a lot. The viscosity of the human blood becomes a lot more significant. My question for you is like, how close are we from reaching that the limit where we have to increase the field to such an extent that the microrobot becomes itself just the system becomes an induction heater? I mean, have you analyzed the effects of like the bandwidth you have to control the robot versus the thermal limit of such a robot? What are the current thinking in that area? Is it just not relevant because the speeds are so slow that it doesn't really matter that much? What's the current statement?
Great question. It's all very, very relevant. It's a fundamental part of what I consider to be the field is understanding these relationships between things like fluid drag, size. Brownian motion starts to dominate. As soon as you get down around micron sizes, a few micron things start vibrating because they're getting knocked around, randomly moving. They're not vibrating, they're randomly moving because of Brownian motion. Some of the mechanics is interesting. So at Stokes flow, you've got fluid drag that is proportional to the radius, not the area, but the radius of the device, which is a problem. Luckily, rotational drag is proportional to the cube of the radius. So that means rotational drag is falling with volume very rapidly as well. And so that's part of the reason why we like these flagella, these rotating things. So there's really an interesting interplay in the mechanics of what's going on at these scales that have to be thought of very, very dramatically. And also then that directly impacts the electromagnetic navigation systems, or the way you're generating the fields. And if you get too small, it doesn't become interesting anymore. I think at nanoscales, we think differently. To me, it's only particularly interesting when I'm in the micron to millimeter or larger scale. But these are, there's a complexity that you've got to think about. That's for sure. So good question.
Yeah. So I wonder what's the spatial resolution for these kind of micro robot can be controlled if two of these robots are controlled individually. For example, can you send two of these robots in a human body and control them? So
so these are one control to many robots. So you've got a professor here, Tim Bridle, right? Tim Brettle, right? So that's one of his areas is. If you had a bunch of robots and you could send one command to all of them, what can you do? And if you know the initial configuration of each one, there is a plan you can generate to get them all to get into a certain configuration. I think that's an interesting problem. But what we do, one of the things we do is we design different classes of these devices, and some of them respond differently to different magnitude fields. And so then we can, make some of them drop out while the others continue. We also generate some resonant frequencies. So you can almost like you can tune some to respond to different resonant frequencies and things like that. Interesting problems, but those are interesting research problems. I think they're a bit of a ways out if we're going to really look at sending these in to dissolve a blood clot or something.
Hi. So similar question to, or I guess maybe even a follow-up to what Joe was saying. As the robots get smaller, and maybe even the catheter case, do you account for, or do you find that you need to account for forces that are already present in the environment, like the magnetic field of the Earth, or like the device itself is this big metal object, right? Is it creating its own magnetic field that you're accounting for, or that you find? Yeah,
we don't worry about the Earth's magnetic field. That's 1,000 times, 10,000 times less than so that's not too relevant. I think the only thing I can say about modeling that there's this framework, I don't know if anybody knows here, called SOFA, if you're familiar with it. It's an open source, it's out of France for soft robotics. And so we've added some magnetic module to that. And so we actually get pretty good results from that. But at small scales, to me, what happens is eventually these things get dominated by Brownian motion, and then it just becomes a kind of a random walk, a biased random walk in a sense, right? So, I think we have a good idea of the physics of what's going on, but it's complicated. It doesn't mean we can solve it. We just know what the effects are for the most part, I think. So.
Hi, Professor. Thank you for the wonderful talk. My question is, I saw the slides. There's an evolution chart, like from rigid to soft to smart to intelligent.
Mm-hmm.
How do you define and distinguish smart and intelligent? And also, what are the current limitations for a microrobot to be intelligent? Yeah. So, what is intelligence? That's a good question. I look at a bacteria, right? Look at E. coli, right? Here's a flagellum. E. coli is about a micron or two long. It has chemoreceptors on it, so it can sense its environment. It can sense aspartate or something that an amino acid it likes. It's got a motor. It's got a chunk of DNA floating in it. That's basically the software telling it what proteins to make to keep itself going, to build the motor and all that. Seems pretty intelligent to me, but it doesn't have a single neuron, right? So I think these are interesting questions that I would love to talk about over a beer. But I think they're, there's definitions of intelligence, I think. To me, if it does something surprising, then I want to explore it and see how I can get something out of it. But it's a good question, yeah. Difficult.
So maybe that's a good question to end on, one that we can all ponder over pizza. No beer here. But let's give Brad a hand. Thanks.
Thank you.